Okay, so if you apply the horizontal line test to the tangent curve, you'll see that it does pass. Okay. So horizontal line test, or the tangent curve, we don't have to restrict the domain to make the inverse a function. Okay. As a matter of fact, when you switch x and y, it just takes this tangent curve and rotates it like this, and you still have a function. Okay. Whereas with sine, we've got to somehow limit it, and so we end up limiting it between -1 and 1. And same thing with cosine. Cosine looks just like sine, just starts at a different place with respect to the origin. So the range, or the outputs for inverse sine, are between -π/2 and π/2. So you see where I have in blue here? Think about this in terms of degree measures or angles. π/2 would be the first quadrant. From 0 to -π/2 would be the fourth quadrant. And so all of my outputs for inverse sine come between -π/2 and π/2. And then for cosine, it's between 0 and pi. That's what I'm drawing a picture of here in green. On here. That's 0 and pi. And for tangent, it's between -π/2 and π/2. So just as a review, the original graph must pass the horizontal line test for the inverse to exist. So we have to limit the domain on sine and cosine in order to have an inverse trigonometric function. To find the inverse trig function, we switch x and y. So what you may notice here is that the domain now here for inverse sine is what we had as the range for sine. Remember, the range for sine was between -1 and 1. We never had values bigger than 1 or smaller than -1. Remember that? And the range is limited between -π/2 and π/2. And the reason for that is that we only want to have unique values of y as outputs. And so we have all the different values, like we have all our different, if you think about the coordinates as we go along here, right here we have √3/2, comma 1/2, and then √2/2, √2/2, and then 1/2, √3/2. Hopefully you can picture those. But all those y coordinates, √3/2, √2/2, and 1/2, get repeated down here, but their signs are different, so they are unique in that way. And then same thing, idea for cosine, but cosine is limited to the first two quadrants. So what I have these up here for is just to call these the x-out zones here. For inverse sine, we're going to x out here and here, leaving just these values in here. So sometimes I'll use either, a lot of students actually will x out the zones that they don't want values coming from. And what you have to remember is you don't want to go through an x-out zone over to the fourth quadrant to give an answer. So remember what I said at the beginning, the learning target is that I will give you the ratio and then the function, and you're going to give me the angle measurement. You would not want to, for inverse sine, give me an answer of something like 7π/4. Because 7π/4 would take you right through this x-out region and this x-out region to get over to here. What you would want to give me is -π/4 as your output, because you'd go from the x-axis straight down to there and never go through an x-out zone. So it's like the burning hot lava. It'll get easier as you go, but you don't, keep in mind, it'll make more sense as we do some practice problems. You don't want to go through the x-out zone to get there. Okay, so you wouldn't, and look at the range here. Is 7π/4 even in the range between -π/2 and π/2? Think about the number line. No, 7π/4 is way the heck to the right of this, π/2. So it's outside of the range. What's going to get x'd out for the cosine here? The bottom two get x'd out, and so you can have all your outputs between 0 and pi. So that one's not a problem. Yeah, and then, well, for inverse tangent, it has the same picture as it does for sine. These should really be, we do have a problem. These should not be closed brackets. Should not be closed brackets. I think I tried to change them. I did it on my notes, but they should not be closed brackets. Do you remember why? What happens on the graph when you put in π/2 for tangent, or -π/2 for that matter? What do you have? Yes, it's undefined. So this really needs to be like this. So change those to open. I don't think I was able to get into that table and change it, so I have to redo the table and change it. So it should be open. All right. Let's draw the graphs of each of these. We're going to draw just one little piece of inverse sine. So here's the way to think about it. If finding inverse sine means switching the x and y, then what I have here is 1 and -1, and up here I have pi over 2 and negative pi over 2. Okay, so think of it that way. I'm taking and switching the axes. I'm switching the x and y, literally. And so at -1, think about -1 here. Here we are in the unit circle. This is 0 over -1 down. What degree measure have I gone through from here to here? And we got to think about the sign. It's negative pi over 2. So what corresponds to negative pi over 2 is -1. We're talking about sine. So I have a dot right here. At -1 to the left, negative pi over 2 down. What about at 0? If I find sine of 0 is, this is the coordinate 1, 0. So sine of 0 is 0. So at 0, I should be at 0. And then if I plug in 1, if I ask what angle will give me a sine of 1, what angle gives me a sine of 1? Pi over 2. Yeah, so I'd be up here at 0, 1. So it's not a line. It actually curves. It goes like this. That is the inverse sine function on the domain -1 to 1. And it is a function if I limit it from -1 to 1. If I let it go beyond -1 and 1, it's no longer going to be a function. Okay. Inverse cosine, we're going to switch the axes. So this is -1 here, and this is 1 here. And right here is going to be pi over 2, and up here is going to be pi. And so the angle or arc whose ratio is 1 for cosine is at what degrees? So, yeah. So the question is, what degree measure in radians gives you a cosine measure of 1? Just at 0. Right? 0. So it's at 1 I'm at 0. I'm going to do some red. What angle gives me a cosine of 0? Cosine of what equals 0 is what I'm asking. Pi over 2. That might be an easy way to do it. And then cosine of what gives me -1? Pi. I know it's reversing the process you've been doing, but this will help you to know your circle better. Sure. It will. So then for inverse tangent, I'm going to switch the x and y. So this is negative pi over 2 here. This is pi over 2 here. I can start labeling this, but remember, the domain is not limited in any way. It's all real numbers, right? So all real numbers, so I can just keep on going. So my tangent curve, I kind of did that for you here. Remember, it was like this, and I knocked it on its side. I didn't knock it on its side the right way here. So let's see, tangent was, I draw the cotangent in that one. So yeah, tangent we have, just go like this. It's kind of like knocking it on its side here. So my graph of tangent is going to look like this. At 0, I'm at 0. And then as x gets bigger and bigger and bigger, I'm going to get closer and closer and closer to pi over 2. So it's going to curve like this. And then as x gets smaller and smaller and smaller, it's going to get closer and closer to negative pi over 2. So yeah, it's just knocked on its side, so it's been turned. So that's what the inverse tangent curve looks like. So inverse sine, inverse cosine, and inverse tangent. So the curves look like. And what I'm going to ask you to do is to evaluate these. And so remember, you're going to be giving me the angle measurement in radians, okay, that corresponds to the ratio. So you could still use your unit circle. What you'd be doing on your unit circle is you'd find, if I ask for inverse sine, for example, here, you think about your unit circle. Let's draw your unit circle here, or draw a circle. So here we have inverse sine. What I have a lot of students do is they will X out the zones that you can't be in. So remember, for inverse sine, it's going back up here. These are the X out zones. It's quadrants 2 and 3, so they'll go like this right away. So that's what they'll typically do. And then we've got to find, this is in words asking for the arc whose sine is 1/2. That's what it's asking for. The arc or angle whose sine is 1/2. So you look at your unit circle. What are you looking at, the x or the y coordinates? Y. And you find the y coordinate either in this quadrant or this quadrant that is equal to 1/2. There will only be one. Okay, because down here it's equal to -1/2. So what is the arc whose sine is 1/2? We draw a picture here. It's right here. I'm trying to make it look low on the circle. What degree measure is that? 5/6. And that's it. 5/6. That's it. So what I'm asking you to do is see what we've done. We have these equations. We have y equals sine of x, right? When it comes to finding the inverse, what we do is we switch x and y. Right? So we do switch x and y. And then what we have to do is solve for y. Well, the way we solve for y is we take what's called inverse sine of each side. Okay, inverse sine looks like this. Sine to the -1 of x equals inverse sine of y. Well, what does inverse sine of y equal? Inverse of a function cancels it out. It could be like taking log base 10 of 10 or something like that. It cancels it. So inverse sine of sine is just y. And so this is y equals inverse sine of x. And so that's what I'm doing here, is now I'm plugging in as my domain the ratios of the sides of the right triangles, and you're telling me the angle that it corresponds to. So, number 2. First thing we want to do is go ahead and X those out. Let's draw a picture of where the arc whose sine is -√2/2 is. Where would that be? First quadrant or fourth? Fourth. And where would it be in relationship to the two axes, the x and y? Yeah, right in between, right? Which is a pi/4 multiple. Okay, but I can't use 7 pi/4 as my answer. Yes. You have to go straight there without going through. You cannot go through an x out zone. You can't go around over here to 7 pi/4. Is it equivalent? Is it coterminal with 7 pi/4? Yes. But is it the correct answer if I'm asking for the functional value of inverse sine of -√2/2? No, it's not. Because when I'm asking for the functional value, which is what I'm asking for here, it doesn't say that, then it's built into it that I want a value between -pi/2 and pi/2. You with me? And 7 pi/4 is not between -pi/2 and pi/2. So -pi/4 is correct. Okay. Let's try a few more here. What about, I'm going to erase this. What about inverse cosine? I'm going to X out. So I want you to tell me the arc whose cosine is 0. I was fast. How'd you get it so fast? Okay, because what am I thinking about here? X's, yes. And so I'm looking for an x coordinate of 0, and so that's how you did it so quickly. It's right at pi/2. So my picture would look like this. I would just draw a ray going up here. and that is pi over 2. Arc whose cosine is 0 is what I'm asking for. You might want to put this in quotes. This is what I'm asking each time. The arc whose blank is whatever the input is. Okay. So here I'm asking for the arc whose tangent is negative root 3 over 3. Now these are a little harder. So X out zones for tangent, you remember what they were? Okay, so unfortunately this is not a multiple of pi over 4. That would be if it were 1 or negative 1. This is a negative root 3 over 3. So now we've got to think about this a little bit. How do you get root 3 over 3? You either get root 3 or you get root 3 over 3. So what does this have to be in terms of sine and cosine? Because that's the definition of tangent. So sine over cosine, we would have to have which on top? The 1/2 on top? Or the root 3 over 2 on top? 1/2 on top. Okay, we've done enough of these. Yes, this is the one that gives you the root 3 over 3. Yes, you're correct. If it's switched around, it will be just root 3 and the 2's would cancel out. So what angle measurement is going to give me the 1/2 on the top corresponding to the sine? When the sine is 1/2, it's lower on the circle or not as far away. So it's the pi over 6 multiple. The pi over 6 multiple, right? It's going to be negative pi over 6 because, let me draw a picture here. We are, because of this negative sign right here, we've got to have a mixture of the signs. So this is what my picture looks like here. My ray is right down here, 30 degrees down, or negative pi over 6 down. You might want to even note on here, this is like a 30-degree reference angle. That's it. All right, any questions coming up as we're looking at this? I'll keep drawing some pictures and do some more of them here. All right, so here, x out, negative root 3 over 2. Is that in the first quadrant or second? Second, and is it up high or down low? It's going to be low because it's farther out than it is up. Okay, farther out than it, because root 3 over 2 is bigger than 1/2. So if you look at your unit circle, down here you're going to have negative root 3 over 2, comma 1/2. It's going to correspond to that. So there's my picture right there. So what angle is that? That's 5 pi over 6, yeah. So now what you're starting to do is make a reference. 5 pi over 6 goes with negative root 3 over 2 when it's cosine. And it goes with 1/2 when it's sine. This one I like. I like the inverse tangents of 1 and negative 1. We can handle those. So where's my ray going to be? In the first quadrant or fourth? First. And is it in relationship to the x and y? Splits it right in half, right? So there's my picture. What angle is that? Pi over 4. So those are the good ones. I like those. These aren't bad either. Inverse sine. So inverse sine, I go x out, x out. So where is it? Arc whose sine is negative 1. Yep, I'm going to do a different color here. Yeah, it's right here. And what is that angle measurement? It's negative pi over 2. We don't want to use 3 pi over 2 because that would be going through the x out zones to get there. If I go 3 pi over 2, I'm going around this way. Negative pi over 2, I go straight there. Okay, don't pass through an x out zone. And because my range is between negative pi over 2 and pi over 2. So 3 pi over 2, just write this down. Think about this. Here's negative pi over 2, here's pi over 2. 3 pi over 2 is this direction. It's outside of that range. It's bigger than pi over 2. All right. This will help you to understand, I think this next page will help you to understand a little bit more about how inverse trig works. So No grumbling. So inverse sine of sine of pi over 3. Inverse sine of sine of pi over 3. This is good. This is good review. Okay. So when we do a composition of functions, where do we usually start when we're doing like f of g of x, and I want to plug in 3 for x? What am I going to do first? F of g of 3, I would do plug 3 in for x in which function? G. And then I would go from there and plug it into x. Same idea here. Okay? So this is like taking f of g of pi over 3. Okay? F is inverse sine, g is sine, and so we're going to start from the inside and work our way out. So what is sine of pi over 3? This you should have.
1/2.
Sine of pi over 3 is not 1/2. Pi on the circle. 3 over 2. Well, we can draw our first picture would be, okay, here's pi over 3 up here. What's my y coordinate when I'm up there? It's 3 over 2. Then I got to draw another picture with my x out zones, because now I'm asking you what is inverse sine of root 3 over 2. So x out, x out. So where's my picture going to be here? Arc whose sine is root 3 over 2 is up here again, right? Yeah. So what's the angle that goes with it? Pi over 3, good. So, what observations are you making here? They cancel each other out. Now you got to be careful though. Okay, guys, you have to be careful. Yes, because sine. Okay, pi over 3 is in the first quadrant. Is that in the any of the x out zones? No. So they cancel out perfectly. Now we're going to get to an example in which it's not in the. It's actually in the x out zone, not in the. It's not actually in the correct region. So, for example, here. Okay, let's do this. 5 pi over 4. Where is 5 pi over 4 located? Which quadrant? Third. Fourth would be 7 pi over 4. Got to remember it's 2 pi all the way around. So 8 pi over 4 is all the way around. So 5 pi over 4 is in the third quadrant. There's a problem there, right? 5 pi over 4, yeah, if I go, okay, inverse sine, don't write this down yet, but if I wrote down arc whose sine is, well, it won't matter here, but you can't just cancel these out and say that 5 pi over 4 is your output, because 5 pi over 4 is not in the range of inverse sine, right? It's in the x out zone. So here's what we have to do. Let's draw this. X, that reminds me it's over there. What value of sine would be equivalent to this one, but it's not in the x out zone? First of all, let's write down the correct, what's the value here? What's sine of 5 pi over 4? We can do that. Negative root 2 over 2. Where do I have an arc whose sine is negative root 2 over 2, but it is actually part of the domain? Yeah, negative pi over 4, that's right. So this is the angle we have to sweep through to get an arc whose sine is negative root 2 over 2. So it's negative pi over 4 is correct. You cannot just cancel these out and write 5 pi over 4 as your answer, because 5 pi over 4 is not between negative pi over 2 and pi over 2. 5 pi over 4 is a bit to the right of pi over 2, right? 5 pi over 4 is bigger than pi over 2. It's outside of that range. All right. What about the next one here? Sine, can we do sine of 2 pi over 3? What's sine of 2 pi over 3? Which quadrant am I in? Second. And am I high or low? Okay, good. So what's inverse cosine of, okay, what is this value? What's sine of 2 pi over 3 going to equal then? 3 over 2. Okay, good. So now we've got to do our little x out zones here for cosine. So what is the arc whose cosine is root 3 over 2 going to be? It is pi, yes, it's low on the circle here. That's pi over 6. Okay, that's pi over 6.
Why couldn't you just leave it like that?
What's that?
Oh, cosine.
Cosine. Yeah, I had a mixture of cosines and sines. All right, number 11. Inverse sine of cosine of 7 pi over 6. So let's draw a picture for 7 pi over 6. You know which quadrant 7 pi is? Such a good review. It's a third. 7 pi over 6 is third quadrant, right? And it's closer, I kind of exaggerated there, it's closer to the x-axis, right? So what is cosine of 7 pi over 6? Negative root 3 over 2, yeah. Good. Negative root 3 over 2. Now we got to ask the question, okay, arc whose sine is, okay, for sine I got to cross out here and here. Arc whose sine is negative root 3 over 2. So where is that little ray going to be? Arc whose sine is negative root 3 over 2. Which quadrant is that in? Fourth. And is it farther down or not as far down? It's farther down here, yeah. So what is that angle? Negative pi over 3, yeah. Negative pi over 3. I'm trying to exaggerate. It's beyond the pi over 4 angle down to pi over 3. It's the big one. Inverse tangent of cosine of pi. So let's, first of all, what is cosine of pi? Can you do that without even a picture? Negative 1, good. And then arc whose tangent is negative 1. Maybe we better draw our picture here. With x out zones, we've got, for inverse tangent, we x out there and there. Arc whose tangent is negative 1. It's going to be right there. What is the arc whose tangent is negative 1? Negative pi over 4. Arc whose tangent is negative. If it's positive or negative 1, you're talking about inverse tangent. You're at the 45-degree angle references, because that's when you have root 2 over 2 over root 2 over 2. All right, what if, okay, this ties in, this is like the questions on the quiz, 3 and 9 on the quiz, and then you have these towards the top of that review. What if I ask for the arc whose sine is 5 over 13? Now I'm no longer on the unit circle. You recognize that? What's the radius of the circle I'm now on? What is the radius, or at least once it's reduced, what's the radius of the circle I'm now dealing with? Or the hypotenuse of the right triangle? 13. So it's no longer a unit circle because that's the 13 is my radius, right? So if I draw my picture here, let's do this. So we're going to x out here and here. So arc whose sine is 5 over 13 is telling me that the, let's see if I can try. It's actually not quite that far up. So the radius is 13. I'll move out of the way here. And so the radius is 13, or the hypotenuse of the right triangle is 13, and the opposite is 5. My angle theta is over here. So before I can do this, what this is right here, you have to understand this is an angle. And so I'm asking for the tangent of a specific angle. That arc whose sine is 5 over 13 is an angle or arc. Okay? So my final answer is going to be a ratio. And my ratio is going to be based on the tangent definition. Tangent of an angle theta is equal to opposite over adjacent, right? I know my opposite is 5. I don't know my adjacent. It is 12. How'd you get that? Pythagorean theorem, or if you remember, it's a triple. So it goes back to finding all the pieces of the right triangle, which you will be doing on your test as well. So what I'm asking for here is tangent of some angle, and that angle is represented by inverse sine of 5 over 13, is equal to, I'm in the first quadrant, so it's positive. Opposite is 5, adjacent is 12, so that's my final answer, is 5 over 12. Then this last one, just real quickly here. Arc whose tangent is 1/2. So arc tangent, I'd x out here and here. So arc whose tangent means the opposite side is 1, and the adjacent is 2. There's theta. And so 1 squared plus 2 squared equals r squared. So r equals square root of 5. So using the Pythagorean theorem, I have all my pieces. So it's asking me for sine of some angle that is represented by an opposite and adjacent in the ratio of 1 over 2. So remember, this is just like asking for sine of some angle theta, if you want to think of it that way. So sine of theta would equal, it's actually opposite 1 over root 5, which would simplify to root 5 over 5. Yeah. So let me give you this now. So on Thursday, you can come in, ask maybe a few more questions on the test. And then after the test, you can work on this. So this it wouldn't actually hurt to work on it between now and the test, too. It'll help. What was that? It's one of those worksheets with lots of problems on it.
Sarah Wilbur, please call extension 1028 from the school phone. Sarah Wilbur.